I'm now going to move on to a new topic. This is the topic of memory hierarchies or cache hierarchies. And before I get into the details, let's just remind ourselves of what our basic 5-stage pipeline does. So the first stage is the instruction fetch unit, where I access the instruction memory and bring an instruction. Then I analyze that with decode, read any register values, move on to the ALU unit, then access the data memory if required, and then finally write my result into the register file. So there are two units here, one where I access instruction memory and one where I access data memory. That's going to be my focus for the next few videos. So that's basically me accessing values sitting in memory, and I'm going to try and make that access more efficient by designing what is called a cache hierarchy. If you look at your system, here's my motherboard inside my desktop or in my laptop, let's say. At the heart of my system is my CPU or my processor chip. We spent all this time designing a pipelined processor and introducing out-of-order execution and doing all of those fancy things. All of that represents a small fraction of the area on my processor chip, right? So that's a single core, let's say an out-of-order core, sitting on my processor chip or on my CPU chip. Now, when this CPU chip does a load or a store instruction, or when it's trying to fetch an instruction, that instruction or that data element is sitting in memory. And this program, may be accessing many, many gigabytes worth of memory. And all of that memory cannot fit on the CPU chip. Okay, so all that memory is placed on other chips which are external to this CPU chip. Okay, so you have a wire coming out of this processor chip, and plugged into those wires on the motherboard is what is referred to as a memory module or a DIMM. And this DIMM has a number of memory chips on it. Right, so all of those memory chips put together can support a very large memory capacity, let's say 16 gigabytes worth of memory capacity. So all the data that a program deals with, or the entire program itself, is stored on this DIMM over here. But accessing this memory takes a large amount of time because this is a technology that is optimized for high density and low cost. So accessing any element from the memory is slow. You're also constrained by the low bandwidth of the set of wires that connects the memory module to your CPU, right? And so getting anything from memory can cost as much as 300 cycles. Okay, so that's really slow. Every time I have to get an instruction here or access a data element here, if I spend 300 cycles doing it, that's going to lead to many, many stall cycles, right? So all of those optimizations that I did to improve my CPU are not going to be very useful if I'm entirely constrained by the high cost of memory access. Okay, so I need to make that a little bit more efficient. So the way that is done is a portion of that memory is stored on the CPU chip, right? So there's all this extra space left over on the CPU chip where I implement what is called a cache. And it could be maybe a few megabytes at most in size, right? So maybe I implement a 1 megabyte cache, which says that every time I touch data for the first time, I have to go to memory, spend 300 cycles retrieving that data from memory. And once I've brought it into the CPU, I kind of keep it around in this cache. And so if I were to touch that same data in the near future, I don't have to go all the way to memory. I just get data by accessing the cache. And accessing this cache is much faster than going off chip and retrieving it from memory. So that's the whole point of introducing a cache on the chip. It's saying that I'm going to hang on to data I've touched recently. I'm hopeful that I'll touch that data again. And if I do, then I can service that request much sooner by getting the data from the cache. And that reduces my overall stall cycles. And you've all seen a similar concept with your internet browsers as well. So every internet browser also has a cache where you keep track of the recently touched web pages. So if you were to touch the same pages again in the near future, instead of spending time and going over the network and getting it from some remote data center, you can get those same web pages from your local file system, right? So that's the whole point of having a cache for the internet browser as well. And this is basically the same concept, but being applied to a processor chip and the memory that your program accesses. So this is what your memory hierarchy or your cache hierarchy kind of looks like. So here's my CPU at one end. The CPU basically does operations on registers, right? So the register in some sense is also like a cache, saying that the data that I expect to touch in the near future has already been prefetched and placed into registers. So when I do add operations, I'm only working with this so-called cache which is my register file, right? So I'm only dealing with registers, and the register is a very small set of values. So it's a very small amount of data, usually less than 1 kilobyte in size, and can be accessed in a single cycle. Then if my value is not sitting in a register, then I have to do a load, make sure that the value is brought into the registers. And so when I issue a load, it's supposed to get that value from memory and then bring it into the register. But on my way to memory, I check two other structures in this example, where I first check my L1 cache. And the L1 cache is about 32 kilobytes in size in this example, so it's a little bit bigger, and it takes 2 cycles to access. So if I'm lucky, I find data here, and then I move it from here into the register file. If I don't find data in the L1 cache, I move to the next level. I move to the L2 cache. Instead of just looking at the most recently accessed 32 kilobytes of data, I look at the most recently accessed 2 megabytes worth of data. So this is a much bigger storage unit, and that increases my chances of finding the data that I'm looking for in this L2 cache. Because this is a larger structure, it also takes longer to access. So I'm going to spend 15 cycles trying to find this data in the L2 cache. If I'm lucky, I bring it into my register. I also bring it into my L1 cache. That way, if I revisit this data in the near future, I can service a request in as little as 2 cycles. Now, if I don't find data in the L2, now I have to go off chip to my memory system, right? So this is the boundary. Everything on the left is on my processor chip, and everything to the, this is on chip, and everything to the right is off my processor chip. So if I don't find data on my chip in either the L1 cache or the L2 cache, now I'm going off chip, going to look up memory, find the data here, bring it into the register. At the same time, I put it into my L1 as well as my L2 cache. Now, sometimes I even run out of memory, right? In this example, I have only 1 gigabyte worth of memory, and the program might be accessing data that is much bigger than that as well. So if I need more data than what is being provided by my memory system, then some of the portions of my memory, some of the pages in my memory, which I've not touched recently, are moved away into the disk, right? So what is the disk? The disk is also called the hard disk drive. It's got a much larger capacity, several gigabytes, even terabytes in size. And because it is made up of mechanical parts, accessing it is also much slower. So accessing something on disk could take a handful of milliseconds, which corresponds to millions of CPU cycles. Okay, so the disk has a much larger capacity. So if I run out of memory capacity, I can move some pages from memory onto the disk. So I have a special space on the disk which is reserved for these memory pages. It's referred to as my swap space, or the swap disk. And in addition to that, the disk also keeps all of my files. All of the stuff that I want to keep permanently are stored in the disk, because this memory is volatile, which means that if I unplug my system, everything in memory disappears. But when I unplug the system, things on the disk actually persist. And so this is where I store all of my files, and this is where my documents will be found, and so on. So this is referred to as the cache hierarchy, where from the CPU, as you move further away, the capacity of each storage structure increases. Its latency also increases. And you're hoping that you can service your requests by finding data in the earliest levels of this hierarchy. In the future, these hierarchies are most likely going to get deeper. So I only showed you a 2-level hierarchy on the chip. There are processors today where you can have an L3, you can even have an L4 cache. And if you don't find data in any of these caches, only then do you go and access memory. Even the off-chip hierarchy is getting deeper. So there are some systems today which may have what is called an SSD or a flash drive between the memory system and the hard disk drive, right? So this could be flash, and it has latencies which are a few microseconds, right? So this is much slower than accessing memory, but it is much faster than accessing the disk. And it also has a storage capacity that comes somewhere between the memory capacity and the disk capacity.